Hello everyone, my name's Warren Black. I was the senior marker responsible with a team of very, very good markers for question 13 of this year's Extension 1 HSC paper. So just in general, before we move into the particular parts of the question, there were a lot of students who did very well overall in this question. I was pretty impressed with that. However, at first sight, the question did appear to be a fairly straightforward question for something as far through the paper as question 13. But what ended up happening was, and hopefully you'll see this from my presentation, there are a lot of small details which really did a great job of testing students' deeper understanding. And it really did a pretty good job of discriminating between different types of students. So overall, my impression was it was an excellent question because it allowed really, really good access for every student. There were very few non-attempts or anything like that. So students seemed to know what they were trying to do, but there was enough trickiness in there to mean that not everyone just automatically got full marks. The other thing that I really recommend you watch out for as we go through the presentation is that in parts A, B, and C in particular, they were sort of like your application type of questions. There were a lot of students who came up with answers that were just totally illogical or contradictory to other things they'd already found. And they didn't seem to notice. Now, that's from our point of view as a marker. There may be a couple of reasons for that. One is maybe they just made an error and they just weren't thinking. So I would recommend that we try as classroom teachers to encourage our students to think more deeply about what they are discovering. But it may also have been that time pressures were playing a little bit there, and they might have known that they'd made an error, but unfortunately didn't have the time to think about it and just rushed on to question 14. So I'm not sure about that. I'm willing to give them the benefit of the doubt. Okay, so here we go. Here's question 13, part A. Again, pretty much a standard sort of question at first sight. So we've got two volumes of revolution there, and we need to find the volume between them to get the volume of concrete to make this sculpture. And here's the solution. These solutions that I'm offering you here are the ones provided to us by NISA. So not necessarily exactly how I would have done things, but I'm happy with this solution. You'll notice here they've drawn a diagram. I'm going to refer to this in a second. It was very, very important that students drew diagrams. The NISA solution offers an outer volume and inner volume, and then they've done the outer minus the inner over here on the right and worked it through to get the 3 pi on 2 for the correct answer. So that's the solution. I'll leave a smaller version of that while I go through some comments here. So in general, the majority of students had a really good understanding of what was required, but lack of depth of understanding meant that there were plenty of small errors made. And as I said a second ago, a diagram is invaluable. The students who didn't draw diagrams typically made errors, whereas the students who did draw diagrams often avoided the errors. So what were the common sorts of errors? Well, first up, correctly identifying the expressions for the inner and outer volumes. Now, what I'm talking about is these two expressions here in the solution. For those of you who have taught the old Extension 2 course, thinking about volumes of revolution and getting a disk here is the way that I still teach the course myself. I would look at this and say, okay, the disk for this outer one is pi times the radius squared, and the radius is the x, so it's pi x squared, which makes it pi y. And similarly for this one, for the inner volume, it's going to be pi x squared again, because the radius is in the x direction, and that x squared is going to be y minus 1, which generates that. A lot of students were not able to get the pi y or the pi y minus 1 expressions because they weren't quite sure about how to do that. For those of you who don't know the old Extension 2 course, I would recommend potentially trying to find a teacher who has taught the old course and just have a bit of a chat to them about how volumes of revolution were done in the course. Now, the other really, really major problem was getting the limits for integrations incorrect. And the common one was that this particular second one here went 0 to 2. And this was the main problem with not drawing the diagram, because if I just go back to the question, students just looked and said, okay, the whole thing goes from 0 up to 2, and they made the limits on both terms 0 to 2. And of course, if they didn't get that right, their answer wasn't going to be right. Now, what that then led to was this third dot point here, questioning their working when they went and evaluated. Now, this thing here is the inner volume, obviously. And if you do that from 0 to 2, I'll let you guys do it on paper for yourselves at your leisure. But if you did that as a 0 to 2 integration, you got 0 for that term. And clearly the inner volume can't be 0, but a lot of students just sailed on regardless, ended up with this 4 over 2, which is a 2. Yep, the volume is 2 pi, not realizing that their outer volume was 2 pi and the whole thing was 2 pi. So that's one of those examples I was talking about. Maybe they didn't have time, but from my point of view, watching their work, it seemed like they just weren't thinking. And then the final comment here is that some students didn't really understand how to generate a volume of revolution about the y-axis as this question was set up. And so they tried to set things up using usually inverse functions around the x-axis. Now, there were some students that I saw I marked 500 and something papers. Most of my markers marked about 1,000. So in the 500 that I marked, I saw some students who managed that correctly using inverse functions, but mostly, as you can imagine, that led to trouble for the students. Now, at this stage, I'd love to ask for questions, but you're not sitting there in a lecture theatre, unfortunately, so I'll just move on. So here's part B, which is the projectiles question. A pretty standard projectiles question, really, without reading it all to you, because you can read that for yourself. They were given the displacement vector, and here it is. A very, very important point is this first little phrase here, where it says an object is projected from a point h meters above the origin. A lot of students miss that, and the connection to this: ball leaves their hand 1 meter above the floor. So you'll see that in a minute. But other than that, all of the numbers and so on to go into this displacement vector are given here in this second paragraph. And then the answer is given. And this is important in a show question. They tell them that the ball will not hit the ceiling, but it will hit the far wall. Okay, so please take note of that without me reading the lot to you. All right, here we go. Now, obviously, it's sort of like a two mark questions here, and there are so many different ways it can be done that I'm not going to bore you to death with all of the different solutions. You'll see them if you look up the markers guidelines when they're published on the NISA website. If not, they're not too hard to work out for yourselves. So I'm not going to show them, but common methods. The first thing that was pretty common, as you can imagine, was to use the displacement vector here to get a velocity vector, get velocity in the j component direction, and from there work out the time it took to get to the maximum height, which was 0.6 of a second or 3/5, and then working out the maximum height to be 2.8 meters from there. So obviously the max height's 2.8 meters, it doesn't hit the ceiling, which is 3 meters up. Or this was pretty clever. I was impressed with students that did this. They allowed the vertical component of the displacement to be 3. So again, that's this term, the j component. They allowed that to equal 3 after they'd made the substitution. They solved or they looked at the resulting quadratic equation and discovered that the discriminant was going to be negative. So then it wasn't possible for that displacement, that vertical displacement, to be 3 meters. That was a pretty good way of doing it. Okay, so that dealt with the ceiling issue. Then we had to deal with the hitting of the wall at the far end of the room issue. So some students would figure out that the j component of the displacement could be 0 and get the time of flight from that, and there it is. And then work out what I'm calling it the unrestricted horizontal range, so no wall in the way to restrict motion. the unrestricted horizontal range ended up being 14 odd metres, and that meant that if it was going to fly 14 metres, then it probably was hitting the wall, or was definitely hitting the wall at 10 metres beforehand. Other students chose to work out the horizontal displacement here being 10 metres and finding the time for that, and got some version of these two, and then substituted that in to get the vertical displacement to be around about 2 metres. So obviously at that time, after it was 10 metres away from the launch, it was still 2 metres up, so it was obviously going to hit the wall. And then the other method that some students used was that they did both of these times and said, well, hang on, it's going to be, it's going to take 0.96 of a second to make 10 metres. And if it kept flying and hit the ground, it would be 1.3 seconds. So clearly it's hitting the wall before it would land. So there was a combination of all of those different methods that we saw. They were all great. There was no problem with any of them. It just depended on which method students chose to use. Okay, now issues. And you can see I've got quite a lot to say here. First up, a lot of students did very well at this question. As you can imagine, there was no real trickery in it. Some students, as per usual, even though the question says do not derive this, chose to start with acceleration and derived the velocity and displacement vectors. Obviously, that takes them a load of time, and the instructions say don't prove it, but I guess they've been well taught and they think that that's what they need to do. But please encourage your students to not waste their time on that. Other students didn't realise that all of the necessary numerical values were included in the question. And so they didn't go and make the substitutions that they really should have. And that made it a little bit harder because they were doing everything algebraically. And so we saw some algebraic errors there. And the launch angle was 30 degrees. So that meant we ended up with a sine 30 and a cos 30 in those equations. And again, some students didn't simplify those to a half and root 3 on 2. And so they were carrying those through and just making silly errors associated with having more complicated equations than were necessary. Interestingly enough, the use of the Cartesian equation showed up relatively frequently. Obviously, this means to me a couple of things. There are plenty of teachers out there that are teaching it just in case, which is probably wise. You know, we're still getting used to the new syllabus and so on. However, it wasn't really necessary in this question. And what tended to happen was that the students who did use it got themselves a little bit confused as to what they were finding. So instead of separating the question into two individual 2 markers, they were doing the whole lot in one off the Cartesian, and sometimes they weren't sure what they were actually finding and therefore making errors from there. And then final little comment that I want to make here, the rounding of decimal results didn't really cause any issues with being right or wrong with regard to the question. But it was very, very disappointing to see how careless students were with their levels of accuracy in a question like this. Now, I marked a question a couple of years ago where accuracy was important and it did matter, and students did have trouble because of their lack of accuracy. And I would really encourage teachers to encourage students to learn to maintain accuracy, save decimal answers into the memories of their calculators, and keep accuracy until the final answer. And then when they round off, actually say, I've rounded this off to 2 decimal places or whatever, just to cover themselves. But as I said, in this question, it didn't really matter. Okay, now, common issues then. I've mentioned some of these already. Quite a few students didn't recognise that the h term in the displacement vector equated to that launch height of 1 metre. And so obviously they were making errors based on not including that correctly. One of the things that was pretty interesting to us as markers was that a lot of students chose to double the time to max height, that 0.6 seconds, and say that was the time of flight. Now, there were some students who thought really carefully about it and realised that at that 1.2 seconds, the ball will be returning to a height of 1 metre and correctly worked the question through. But there were plenty of students who judged incorrectly that that was the time to get the range, and they worked out an incorrect range at 1.2 metres, which caused them grief. So it would be worth talking to students about the symmetry of those situations and how to counter the symmetry when the launch is not from a zero vertical displacement. And then again, I mentioned this previously, we saw plenty of contradictory results. One of the really common ones was that the max height was 2.8 metres, and then the height at displacement 10 metres was, say, 4 metres or 5 metres or something like that. So higher than what they had already determined the max height could be. And as I've said, not a lot of thought went into this, or not a lot of noticing that they had a contradiction. So there wasn't much going back and correcting. But as I said, maybe time was the issue there as well, and they decided they'd be better off moving on. Other little issues, some students obviously didn't read the question carefully enough, and so they only completed one part of the question and then moved on. So they might get the max height was 2.8 metres and say, great, it doesn't hit the ceiling, and then that was it, they would move on and not deal with the wall issue. And then, as you can imagine, show questions, the students know the answer. So as per usual, they need to show enough working to justify the result. Sometimes they'll come up with a minimum of working and then say, therefore, it doesn't hit the ceiling. And I'm not convinced that they actually knew that, and full marks can't be awarded there. Okay, so that was our projectiles question. I'll move on now to the area question. And again, this question doesn't look on the surface to be too hard, but I'm thinking that you'll see that there were a lot of silly errors that were made by students because they just didn't quite understand all of the small details of the question. So there it is. And here's the solution, again, provided by NISA. They've used symmetry to say that the two halves will be the same, so let's just work out one half. Personally, I would have put the 2 in front of my integration sign and just said the area is 2 lots of this 0 to 2, but whatever, doesn't matter. Do take notice of this. They've done top function minus bottom function, which worked quite nicely. A lot of students very, very sensibly separated and did the top as triangles and then the area under the bottom as an integration. That worked beautifully, but without care, it did lead to some errors, which you'll see. So the answer here was 2 pi. I'm not sure if you realised, but one of the common answers that we saw in question A was also 2 pi if they got the 0 for that internal volume. So we saw a lot of 2 pi's in this question 13 overall, which we had to be careful with. Okay, so here we go, comments. Majority of students had a good understanding of what was required, but plenty of ways to make errors. Inconsistencies again weren't noticed. So for example, one of the common things, if you look at the triangle above, plenty of students did half of the base 4 by the height 2. So half of 4 is 2, 2 2's 4. So they got the area here as 4 square units, and then went through and doing one of the common errors, came up with an overall area of 8 minus 2 pi. Now, of course, 2 pi, let's call that 6. 8 minus 6 is 2. So they've got an area of 4 up here and an overall area of around about 2 and haven't noticed. So there's one of the common inconsistencies. There were plenty of them in this question, but that's a common one to give you an example. Okay, so common problems. Lack of use of symmetry, particularly with respect to the triangular area. Now, what that means is they were trying to integrate, say, from -2 to 2, the absolute value of 2 minus x, which meant that when they dumped incorrectly the absolute value signs, they were actually getting the line, I'm just trying to get my mouse alive here, getting the line running all the way up here. And of course, that didn't work very well for them, as you can imagine. Okay, and of course, this is the same thing really, just not understanding how to deal with the integration of absolute values So sometimes we saw absolute value signs running all the way through the integration and then just disappearing at the end magically. So it's worth having a think about that. I can't remember which year, but a few years ago, I think it was in an advanced paper, there was an integration in a multiple choice question of an absolute value function. It would be a good one to show them as well. Okay, there were students who used the wrong axis to determine the limits of integration, particularly with regard to the curve part here. So we saw plenty of students going from -1 to 0. Maybe they were still thinking about what they had done in part A there, I'm not sure. Okay, not dealing correctly with the area below the x-axis. Now, as I said a moment ago, if they did top function minus bottom function, it worked out nicely. The students who separated into the two parts and said, okay, I'll do a triangle and then I'll do an area here, were often correct in each of their different parts, but then added the two parts together instead of doing the top function minus the bottom function. That's one of the things that would lead to an answer like this 8 minus 2 pi here. Okay, and then working correctly, plenty of students had put absolute values around this term. They'd realised that because it was an area below the x-axis, it was going to be negative, so they'd put absolute values around it. But then they didn't recognise that the absolute value of 4 minus 2 pi had to be turned around to be 2 pi minus 4 because it was a negative value, 4 minus approximately 6. So they ended up with the 4 for the triangles plus 4 minus 2 pi, which led them to this 8 minus 2 pi here. So a little bit of discussion about, okay, how would we deal with an absolute value of something like that's probably worthwhile. As you can imagine, the integration of this 8 over 4 plus x squared term was quite difficult for some students. And so practice using the reference sheet would be recommended there. And then the final thing is some students got to versions of this line here and then unfortunately chose to use degrees. So the inverse tan of 1 came out to be 45, 4 45s was 180. And we saw answers of 360, but sometimes this part was incorrect as well. And we had things like 360 minus 2 and 358 and answers like that. So again, thinking about the question from a teacher's point of view, you look at this and you think, yep, great, that's not too bad. They can access that. And this is on the reference sheet and it's all going to be good. But as you can see, there were lots and lots of little ways for them to make errors and not get full marks there. Okay. Final part of the question, part D, there was a part 1 and a part 2. Part 1, they tell you the substitutions and it's basically start with the left-hand side and end up with the right-hand side. And here's the solution offered by NISA. You can see that they've made the substitution there and then they've used the sums and differences to products formula from the reference sheet to get this. The cos D's will cancel, so will the 2's, and you end up with tan B, a pretty simple result. A lot of students use that method. A lot of students, again, as you can imagine, use just the differences and the sums expansions. So that's not included here, but it works quite nicely. The terms cancel each other. You end up with this as well. Okay, so this question, very well done overall. This is probably one of the better parts of the question from our point of view. However, there were some students that just got tangled up a little bit here and there and didn't provide sufficient working to justify their answer. So, you know, I usually say to students, as soon as you see a show or a prove where you know the answer, make sure you do probably a little bit more working than is necessary. Okay, now common problems, there weren't a lot of them here, but those who did find difficulty often didn't realise that they needed to just make this substitution. The substitution was given here. It was an obvious first step, but for some reason they just didn't see it. So they missed the hint. I don't know why. And then using the reference sheet, you know, it was very, very good, but there were some students who just didn't use the reference sheet carefully enough and made some silly mistakes. There were some poor algebraic processes, not usually with this method, but the ones who use the expansions, the differences and the sums expansions there. And occasionally there were students who, again, they'd be these ones that didn't see the obvious hint, and so they chose to use T formulae. I did see a couple who managed to get that out successfully. However, it was pretty long-winded and time-consuming, and the majority were unsuccessful with that. Okay. Part 2 of this question. I'm going to flick backwards and forwards here, but again, the common problem, as you can imagine, is that students didn't see the connection to part A. Now, take a look at that and then just go back to this thing, and that would be far enough back, but sine A plus sine C, cos A plus cos C, well, there it is. Just got to make the A and the C into those terms there and work from there. This is the NISA solution. They've sort of jumped the simultaneous equation proof here, but you can see the A there and the C, and doing the simultaneous equations works out that the B comes out to be this 11 theta on 14. So now going back to the equation that's given, we end up with tan of B is pi on 3. I think, let me just go back and check. Where was it? Oh, it's root 3, sorry, tan of B is root 3. And so now we can go and solve that and come up with the 2 answers there. Okay, so comments, quite well done really, but there were some students who just didn't see that there was a connection. So, you know, I know that you guys are all teaching students that if there's a part 2, it's got something to do with part 1, and maybe if there's part 3, you do part 1 and 2 and use both of them to get the part 3. I know you're teaching that, but some students still just miss it. Common problems though, quite a few students here would get to the B equals 11 theta on 14 and not realise, okay, that's only a step. If you look at the actual equation that they're trying to solve there, it's an equation in theta, and they were only solving for the B. So they stopped halfway, unfortunately. Some students forgot to find all of the solutions. So we saw plenty of the 14 pi on 33, but not necessarily the 56 pi on 33. So they need to just check the domains and look for the other potential solutions. Algebraic errors just in solving these simultaneous equations and so on. So we did see some errors here. Very common was 11 theta over 7 because this 2 got missed. So that's just a key thing, students rushing. Now, this next one sort of worried me a little bit. Some students correctly solved that, okay, this is B, and so tan of B was root 3, which meant that the B had to be pi on 3. So that was all correct. The unfortunate thing about that was that students who did that often missed the concept that we were dealing with a 0 to 2 pi domain, and they only came up with the 14 pi on 33 answer and missed the other one. And then, as I said previously, some students just didn't recognise the domain was 0 to 2 pi, and they worked in degrees again, like they did in the projectiles, the area question, part C. And so they gave us answers in degrees, even though the domain was clearly specified to be 0 to 2 pi. Okay, now that's it for me. I would dearly love for you to be able to ask questions, but not this year, maybe next year. But I'll just go back to what I said at the beginning. From my point of view, a very, very good question because it was accessible to the majority of students, but it had enough small nuances in it that meant that without really deep understanding, students weren't going to get the full marks for everything. So I congratulate the exam committee on this particular question. A lot of students did very, very well, which means that they've been taught well and they know what's going on and they do have that deep understanding. But this will be a good question for future years to just show, okay, look, take care, read carefully and watch out for all of the small little nuances that are buried within these questions. Okay, I'll stop there. Thanks very much for your time and good luck this year.